In today's lesson, we're going to study centroids. The centroid of an object is an important physical property that will affect how objects respond to external forces. When forces are applied to objects, we often simplify static calculations by identifying a single point through which we can assume the force acts. The centroid of a 2D figure or even a 3D solid is the geometric center of the object. Technically, you can calculate the position of a centroid by finding the mean position of all points in the object. Go ahead and make sure that you see the symbol for what a centroid is. It's represented right here. An object is in a state of equilibrium if it's balanced along its centroid. Technically, the center of gravity refers to a point at which the entire weight or mass of a body is considered to be concentrated, so that if it's supported at this point, the body would remain in equilibrium in any position. So what is an object's centroid location used for in statics? It's used for theoretical calculations regarding the interaction of forces and members as derived from the centroid's location. It's important to note that one can determine a centroid's location by utilizing the cross-sectional view of a three-dimensional object, such as this I-beam shown below. When dealing with symmetrical objects, a centroid's location can be determined by the object's line of symmetry. Take a look at the bottom example on the left. We have a triangle. The centroid is located along the line of symmetry. When an object has multiple lines of symmetry, its centroid is going to be located at the intersections of those lines of symmetry. So you can see here with the square, we have two lines of symmetry. The centroid is located at the intersection, and the same goes for a circle. Now, anytime you're given a simple shape, such as a square or rectangle, the centroid's location is going to be located at a distance of half its base and half its height. We use X bar and Y bar to represent the horizontal and vertical distances of that centroid. X bar will represent half the base, Y bar will represent half the height, as denoted in the picture. The centroid's location of a right triangle is located at a distance of a third of its base and a third of its height. Again, we'll use X bar and Y bar to represent the horizontal and vertical distances for that centroid, respectively. Again, X bar will be base over 3, Y bar will be height over 3. When given a half circle, also known as a semicircle, the location of a centroid is at a distance of 4 times the radius divided by 3 pi, away from its axis on the line of symmetry. So you can see here in this given semicircle, we have 4 times the radius divided by 3 pi, which gives us an approximate value of 0.8 inches. That 0.8 inches represents the distance from the axis on its line of symmetry. So this distance right here is approximately 0.8 inches. As you could probably have guessed, most objects are made up of much more complex shapes. So we need to be able to calculate the centroid of a complex shape. To do this, you need to start by dividing the complex shape into simple shapes. Once this is done, you're going to want to calculate the area of each of the simple shapes that you created and determine the locations of their respective centroids. To find X bar, which is the horizontal distance to the centroid of the complex shape, we're going to have to take the sum of the products of each individual simple shape's X bar and multiply it by its respective area of that simple shape. Once you do that, then you're going to divide it by the sum of the areas of each of the individual shapes. And then you can repeat this process for each of the other components, Y bar, Z bar. X bar represents the distance horizontally, Y represents the distance vertically, and Z represents the depth of a 3D object for finding the centroid of that complex shape. Here's a sample problem for determining the centroid's location of a complex shape. It's important that you follow each of these steps closely, and I would highly encourage you to write each of these steps down in your engineering notebooks so that you have them to refer back to when doing these types of problems. So step 1, when given a complex shape, you're going to want to divide that shape into simple shapes. Here I've taken this complex object and divided it into 3 simple shapes: a rectangle, a right triangle, and a square. Step number 2, Determine a reference axis. Now, as a rule of thumb, a reference axis, think, is similar to a Cartesian plane where it's an XY axis. We have a reference axis in both the horizontal and vertical directions, horizontal being the x-axis, vertical being the y-axis. To review how to calculate areas of simple shapes, the formulas here are listed. You are responsible for knowing how to find the area of a square, which is just taking the side and squaring it. Finding the area of a rectangle is the width times the height. Area of a circle is pi r squared, and the area of a triangle is half the base times the height. Now in step number 3, we're going to calculate the area of each of the simple shapes. Starting with shape number 1, we have a rectangle, and in order to calculate the area of a rectangle, it's going to be the width, 3, times the height, 6. So 3 times 6 is 18 square inches. Make sure you include your units. Next, shape number 2, we have a right triangle, so it's going to be half our base. So half of 3 is 1.5, times it by the height, which is also 3. So 1.5 times 3 is 4.5 square inches. And then shape number 3 is a square, and we can take the side and square it. So 3 squared is 9 square inches. In step number 4, you're going to determine the centroid's location of each of the individual simple shapes. So in shape number 1, we need to find its centroid's location, which is going to be located at the intersections of the lines of symmetry. So you can see here I have 2 lines of symmetry. Here's my centroid's location. In shape number 2, the centroid is going to be located at an intersection of a third of its base and a third of its height, since this was a right triangle. So a third of its base, a third of its height. And in shape number 3, we have a square. So again, the centroid's location is at the intersection of those lines of symmetry. So we have a horizontal and vertical line of symmetry. The intersection is our third centroid location. Now in step 5, this is one of the most important steps, and it's one that we tend to make a few mistakes on. In step 5, you're asked to determine the distance from each simple shape's centroid to its respective axis, whether it be the x-axis or y-axis. Think of your x-axis as, again, your horizontal axis. Let's write this in, x-axis. And your vertical axis is your y-axis. You can think of this bottom left-hand corner as your origin 0, 0. So in shape number 1, we have a rectangle. So remember, for a rectangle, it's half the base, half the height. So here is the distance from the y-axis to the centroid. That's my horizontal distance. And then the distance from the centroid to the x-axis, that's going to be my vertical distance. So a half of 3 is 1.5. And then a half of the height, well, the height of this rectangle is 6, so half of 6 is 3 inches. For shape number 2, we have this right triangle. I drew in the centroid's location, which is a third of the base, a third of the height. Now the distance from the y-axis to the centroid is going to be my horizontal distance. So we had a third of the base, so a third of 3 is 1 inch, plus my 3 inches gives me my 4 inches for its horizontal distance. And then the distance from the centroid to the x-axis is going to be a third of the height, which was 1 inch, plus 3 inches gives me 4 inches. And then finally, we have our square for shape number 3. So the distance from the centroid to the y-axis is going to be 4.5 inches. And the distance from the centroid to the x-axis is, again, 1.5 inches. Now in step 6, we're going to multiply each simple shape's area by its distance from the centroid to the reference axis. So in shape 1, Recall our area was 18 square inches. I'm going to multiply that by its distance to the y-axis, which was 1.5 inches, and that gives me 27 cubic inches. In shape number 2, our area was 4.5 square inches. Again, I'll multiply it by its distance to the y-axis, which was 4 inches. So I have 4.5 inches times 4 inches gives me 18 cubic inches. And then in shape number 3, the horizontal distance from the y-axis to the centroid was 4.5 inches. Multiply it by its area, 9 square inches, and I get 40.5 cubic inches. Now I'll do the same thing with each of those areas, but multiply it by the distance from the centroid to this time the x-axis. So in shape 1, 18 square inches times the distance from the centroid to the x-axis, which is 3 inches, and I get 54 cubic inches. In shape 2, we'll take our area of 4.5 square inches, multiply it by its distance from the centroid to the x-axis, which is 4 inches, and we get 18 cubic inches. And then in shape number 3, we have our area of 9 square inches, multiply it by its distance from the centroid to the x-axis, which is 1.5 inches, and we get 13.5 cubic inches. When setting this up, I would highly encourage that you make these two tables like you see on this slide. So in step 7, you're going to find the sum of the products of each of those simple shapes areas and their distances from the centroid to the reference axis. So if I add up 27, 18, and 40.5 cubic inches, I get a total of 85.5 cubic inches. And then for the other table that we had, I had 54 cubic inches, 18 cubic inches, and 13.5 cubic inches, which again gives me 85.5 cubic inches. Now, these two numbers will not always match up. It's just a coincidence that it did for this particular shape. So don't always assume that those should always match up. Now in step 8, you're going to take the sum of each of the individual simple shapes areas to determine the total shape area. So the 3 shapes had areas of 18 square inches, 4.5 square inches, and 9 square inches. If I add that up, I get 31.5 square inches. So in step 9, you're going to divide the summed product of the areas and distances by the summed object's total area. So to find x bar, which is the horizontal distance from the y-axis to the centroid of this complex shape, we have 85.5 cubic inches divided by 31.5 square inches, which gives me 2.71 inches. To find y bar, which is the vertical component, or the distance from the x-axis to the centroid, I'll take 85.5 cubic inches and divide it by 31.5 square inches, and again, I get 2.71 inches. Again, x bar and y bar should not always match up. It just depends on the type of complex shape that's given to you. Now, the reason why these two values match up is because there is a line of symmetry that's been drawn in for you guys, and you can see here that cuts this into 2 symmetric parts. Now, I did want to bring to your attention that there is an alternative way to find the centroid of a complex shape. The previous method added smaller, more manageable areas together to make a more complex part. The alternative method that we're going to talk about now is called the subtracted method, which uses the exact same equations, uses nearly the exact same process. The only difference is instead of starting with smaller shapes, we're going to start with a bigger shape that's much more simpler, and then we're going to treat any shapes that need to be removed as considered negative areas. So you can see here, using the subtractive method, rather than breaking this complex shape up again into 3 simple shapes, I'm going to make this one big square, which is going to have the complex shape and then that right triangle in the top right corner, which will become the negative area since we're not going to actually include that space. So shape 1 is the square. Shape 2, we're going to remove the area to get the centroid of the complex shape, which is that triangle. In step 3, we're going to calculate the area of each of the simple shapes. So the area of the shape 1, again, was a square, so it's 6 by 6, or 6 squared, which is 36 square inches. The area of shape 2 is half the base times the height. So half of 3 times 3 is 4.5 square inches. But you need to be careful now. Since this area is being removed, we're going to call it a negative area, so we have to throw a negative sign in front of the 4.5 square inches. Now in step number 4, we're going to determine the centroid of each of the simple shapes. So recall shape 1 is a square, so the centroid is going to be located at the middle of that square, which should be at the intersection of the lines of symmetry. In shape number 2, we have a right triangle. So remember, it's going to be a third of its base and a third of its height. The picture denotes that on the left. In step number 5, you're going to determine the distance from each of the simple shaped centroid to the reference axis. Again, we're going to be doing this from both the x as well as the y axis. So for shape number 1, we have a horizontal distance to our y axis of 3 inches. And then we have a vertical distance from the centroid to the x-axis of also 3 inches. For shape number 2, our right triangle, we're going to have a distance from the centroid to the y-axis of 5 inches. And make sure you guys can see how we got that. So remember, a third of the base was 1 inch, which means if this whole thing was 6 inches, 6 minus 1 gives me my 5 inches. And then a third of its height is also 1 inch. And we want the distance all the way from the centroid to the x-axis, which again should be 5 inches. Again, the whole thing was 6, subtract 1 inch, that's our 5 inches remaining. Now in step 6, we're going to multiply each of the simple shapes area by its distance from the centroid to the reference axis. So in shape number 1, we had 36 square inches. Multiply it by its distance to the y-axis of 3 inches, and we get 108 cubic inches. In shape number 2, we had a negative area, remember, of negative 4.5 square inches. If I multiply it by its distance from the centroid to the y-axis of 5 inches, we get negative 22.5 cubic inches. And then again, for the second table, we'll take shape 1, take its area, multiply it by its distance from the centroid to the x-axis, which was 3 inches. So 36 square inches times 3 inches is 108 cubic inches again. And then for shape 2, that right triangle, we'll take its area of negative 4.5 square inches, multiply it by its distance from the centroid to the x-axis of 5 inches, and we get negative 22.5 cubic inches. Now in step 7, you're going to sum the products of each of those simple shapes area and their distances from the centroid to the reference axis. So I got 108 cubic inches plus negative 22.5 cubic inches, which again gives me my 85.5 cubic inches. And then if I do it again with the second table, 108 cubic inches plus a negative 22.5 cubic inches gives me again that value of 85.5 cubic inches. And those two values should look similar because they match up with what we found using that first process. In step 8, we'll take the sum of the individual shapes areas to determine the total shape area. So the area of shape 1 was 36 square inches. In shape 2, the removable area is negative 4.5 square inches. If I add that up, I get my 31.5 square inches. In step 9, we can divide the summed product of areas and distances by the summed object's total area. So we had 85.5 cubic inches, divide that by 31.5 square inches, and we get 2.71 inches for X bar, and I get the same value for Y bar. 85.5 cubic inches divided by 31.5 square inches gives me my 2.71 inches. Again, those values match up only because that complex shape had a line of symmetry in it, as indicated by the picture on the right. So again, just to reiterate how to find the centroid of a complex shape, to find X bar, you're going to take the horizontal distance from the centroid to the y-axis of each simple shape, multiply it by its respective area of that simple shape, and add those values together. And then divide it by the sum of all the areas of those simple shapes. And then you can do that same process to find the Y bar and Z bar of a three-dimensional shape. For our class and its purposes, we're going to look at just two-dimensional shapes using both X bar and Y bar. Now, most structural elements have geometry that can be divided into simple shapes. Each of these shapes can be considered to be part of a rectangular solid. The shapes above include a rectangle, L, C, box, and I-beam. Taking a look at this L-shaped beam, you can see that we can break that complex shape up into two simple rectangles. Now with the channel shape, which is also known as a C shape, we can take that complex shape and divide it again into three simple shapes. In this case, we have three rectangles. With a box shape, we can divide that into four simple rectangles. And with an I-beam, we could take that I shape and break it down into three simple shapes of three rectangles. To calculate the strength of a structural member, you must first be able to calculate its centroid. If the member is subject to pure bending and its stresses remain in the elastic range, which means that as it bends, it can go back to its original shape, then the neutral axis, when seen in 2 dimensions, or the neutral plane in 3D, of the member passes through the centroid of the section. The centroid is always again located on the axis of symmetry. Now remember that forces push and pull on objects, causing the object to be in tension or compression. The neutral plane is the unstressed region that passes through a structural member and separates the section under tension from the part of the structural member under compression. This concept will lead us into further discussions of both structural and civil engineering.